Okay, so we're ready to continue on with section 8.5, part 2. And so this is projections and also the magnitude of the projection. So first of all, we have our projection. This is a little bit more nicely written, so I just wanted to show the equation. This is the projection of vector A onto vector B. So onto, I really want you to know that word, onto vector. That vector B is the vector that is being projected onto. So notice in our equation here, vector B is written multiple times. We use this vector B in everything we do. So if you can remember, the onto vector is the one that is used the most. That'll help you out the most, trying to keep track of which vectors go where for these equations. So we've got the projection of vector A onto vector B is equal to the dot product of vector A and vector B over the magnitude of vector B squared times the vector B. So everything in the parentheses here is going to end up being a scalar. So just one number. Can be positive, negative, whatever it is. This is going to be just a scalar, a number. Then you're going to multiply that number by the vector B, and then that will give you your projection. So vector B, that's an actual vector, and your answer is going to be in vector form for a projection. Okay? Then when we come down and we need to find the magnitude of the projection, don't go through all of the math of trying to find the projection and then finding the magnitude of this vector here. You should come up with the same answer if you do that. But it has its own simpler equation to be able to find the magnitude of the projection. And it's what they call the component, which is kind of confusing. They talk about, why they can use that word component. But when we call this the component form of a vector, it's kind of confusing. Go back and use that word again. So a lot of times we'll just refer to it back as the magnitude of the projection. But you may see it somewhere along the way in this format. All I really want you to know is this part right here, and you'll notice in the notes that I've done so far, I usually just call that like the magnitude of vector U, where U is the projection. So it's the dot product divided by the magnitude of vector B. Okay, so let's look at this first example. I know this says example 3. When I do this in the classroom, I had a couple of previous examples, same as the homework that you did yesterday, but since I've got all of that instruction on a video that you can go back and watch if you need to, then I'm just going to skip the review examples. So we're starting off with example number 3. It says let vector A equal negative 5, 2, and vector B equal 3, 0. Find the projection of B onto A. So we've got to be careful with this because this is the opposite of the formula that we just looked at. So now we are doing vector B onto A. So A is our onto vector. So A is going to be the one that occurs the most. So we're going to do the dot product of vector B and vector A, so that's finding the dot product, over the magnitude of vector A squared times vector A. So I always write whichever is not the onto vector first. So it doesn't really matter if you did A dot B, for your dot product. The order doesn't matter on that, but I do always try to write them in the order that they say here, so that we always know that the second one of the dot product is the one that's going to occur on top, the one that we need to find the magnitude for, and also the vector that we're going to use in the end again as well. Okay, so first step, let's see, let's find the dot product. So we're just going to over here on the side find all of the little steps that we need. So to find our dot product of B and A, so we're going to have 3 times negative 5 plus 0 times 2, and that equals negative 15. Then the second step, or step 2, we want to find the magnitude of vector A. Okay. And our magnitude of vector A is going to equal the square root of negative 5 squared plus 2 squared, which is going to equal the square root of 25 plus 4, and therefore is the square root of 29. Okay, so now we have all of the little individual information that we need to find our projection. So let's write it out. We've got our projection of vector B onto vector A is equal to the dot product, which we found that dot product, and that dot product was negative 15. So negative 15 over the magnitude of A, which we just found to be the square root of 29, and it's the magnitude squared, which that works out kind of nice, times the vector of A. So vector A is equal to negative 5, 2. Okay, so let's simplify that a little bit. We've got negative 15 over 29 times the vector negative 5, 2. And so my final answer is going to be 75. So negative 15 times 5 is 75 over 29. And remember, this is a vector. And then 2 times negative 15 is going to be negative 30 over 29. And that's my final answer for our projection of B onto A. So when we're finding a projection, we are going to end up with an answer that is in component form of a vector. Okay, next we're going to skip to example 6. So find the magnitude of the projection of negative 5, negative 7 onto the vector negative 9, negative u. So we want the magnitude of the projection. I am just going to denote that as the magnitude of vector u, saying that vector u represents my projection. So the magnitude is equal to the dot product. Now in this case they do not give me vectors that are named, so I'm going to name these vectors myself. So I'm going to use the formula that I had in the beginning. So the dot product of vector A and vector B over the magnitude of vector B. And that's going to be our formula for the magnitude of the projection. And so I'm going to say this is vector A, because the way I have this equation written, B occurs most, so B is the onto vector. So negative 5, negative 7 is being projected onto the vector negative 9, negative 9, so I'm going to call that vector B. All right, so let's find our dot product. I'm going to do all of this work over here on the side. I've got vector A, vector B, and we're going to find the dot product. So negative 5 times negative 9 plus negative 7 times negative 9. And then that's going to equal positive 45 plus positive 63. Add those together, we're going to get 108. Oops. 108. And then we also need to know what the magnitude of B is. So vector B magnitude, the square root of negative 9 squared, which is 81, plus the negative 9 squared, which is 81 again. So we get the square root of 162. Okay, so that means the magnitude of our projection is going to equal the dot product, which we found to be 108, divided by the square root of 162, and then I just figured that out as a decimal, so 8.48528. And that's our final answer. Okay, the last couple of examples talk about work. So when we look at work done is the question here. So if we want to know how much work is done, then we can use vectors to figure that out. So we can look at a force vector, F, and we can look at a distance vector, D. To find out the work that's been done between those two vectors, we just need to find the dot product between those two vectors. So let's look at this cart right here. We have a cart that a force is being applied at a 30-degree angle. So we've got a person that is standing here, and this person is holding on to this rope and walking along this road. So we've got a force that is being applied at a 30-degree angle, and they have discovered that it is 30 pounds of force. So this vector up here is our force vector. This vector down here is going to be our distance vector. So this is how far the cart is traveling. So this cart has traveled 20 feet at this point. We are going to call this our D vector, or our distance vector. Okay, so to find the amount of work that has been done in this situation, we need to find the dot product between F and D. Now we are going to use what we would consider the geometric formula, or formula 2, if you remember back from the notes, where we talked about dot products. That is a dot there, not a minus. And so we have the magnitude of the force vector times the magnitude of the distance formula, or magnitude of the distance vector times the cosine of theta, which, remember that theta is the angle between the two forms, the two vectors. So this is actually what they give us. They give us the magnitude of the force vector, which is 30. They also give us the magnitude of the distance vector, which is 20. So we've got 30 times 20 times the cosine of theta, which I've already calculated all of that. So all of that ends up, do this on your calculator. Oh, whoops, sorry. Let's put what theta is in there. So cosine of 30. Make sure that you're in degrees again for your calculator. Okay. So that whole thing ends up equaling 519.61524. Okay, and that is all we have for section 8.5, part 2.